Okay, so start from today, I will starting to talk about this course, linear algebra. To start with, I would like to introduce some basic concepts about linear equations, and also what is system of linear equations. Okay, so very simple. As you can see that a linear equation, as you expect, it is one equation. Generally, we can write into something like this. Okay. And those A1, A2, A, and B, those are, either real numbers or complex numbers. Okay. But in this class, we will focus on those are real numbers. And also the subscript, those n's, it can be any positive integers. So very simple example, for example, like x1 plus 2x2 equals 3, right? Or, I don't know, negative 3x1 plus 2x2 minus x3 equals, let's see, 7. So those are, linear equations. However, something like this, or and you will see those are not linear equations. Okay, and just keep in mind that to having a linear equation, it must be, the relationship must be linear. And you see that here, the relationship, it's going to be nonlinear. Why? You see, because here it's x2 to the power of 1 over 2. It's not in a linear form, right? And also on top of this, you have x1 times x2 here, also nonlinear. Okay, and a system of linear equation, basically it's a collection, of more linear equations with the same variable. For example, something like x1 plus 2x2 equals 3, negative 3x1 plus 5x2 equals 10, right? So this is a linear equation, very straightforward. And also, the solution of this linear equation, often it's a solution of this system is actually, it's a list, right? It's a list. You can write into, S1, S2, up to Sn. It depends. The number of the variables you have, and if you substitute those back to the system, and then it will make each equation true. Okay, it will make each equation true. Okay, and also sometimes the solution for a system might not be unique. In other words, you may have infinite, many solutions, for a system of linear equations, and the set of all possible solutions it's called the solution set. Okay, and two systems, linear systems, two linear system, we call equivalent if they have the same solution set. Okay, that's very obvious, right? Okay, so those are some very basic concepts here, and some new definition: consistent or inconsistent. First of all, so for any system of linear equations, there are three possibilities for its solution set. So it could be there's no solution, okay? Or it could be one unique solution, exactly one, okay? Or third case, you can have infinitely many solutions, okay? Infinitely many solutions. Now, if a system of linear equations has either one solution or infinite many solutions, we call this system is consistent. Okay. Otherwise, this case is called the inconsistent. Okay. So there are some concepts here. Start with another page. The core part of the linear algebra is to introduce the notation of using this matrix notation, right? So okay, matrix notation. So basically, what is a matrix? So let's start with one example. For example, if you have x1 plus 2x2 plus 3x3, x equals 1, and then, I don't know, negative 2x1 minus 3x2 plus 7x3 equals negative 12, and then, let's see, 4x2 minus 11x3 equals, I don't know, negative 24. If this is the a system of linear equations, right, you have three variables, and then of course on the third one there is no x1 variable, but in this case we can let the coefficient in front of x1 as 0, so the corresponding coefficient matrix, so that's coefficient matrix for this system is going to be 1, 2, 3, negative 2, negative 3, 7, 0, 4, negative 11. Okay, and this is one example of the matrix, and it has 3 rows, 3 columns. So often we will call this is called a 3 by 3. Okay, first one stands for the number of rows. Third one stands for the number of columns. And more we gonna use is called the augmented matrix, which is not too much different. Well, it is a big difference. You will see. So basically, it is the coefficient matrix along with the one more column, and that one more column, which is the real numbers on the right hand side. Our problem is 1, negative 12, negative 24. Okay, so this is what we call the augmented matrix. Okay, so yeah, So that's the notation here. The goal of of this linear algebra courses is trying to solve a system of linear equations, right? But how do we start? Well, the basic strategy is, if you have a very complicated problem, okay, and if you can do something to replace this complicated system to an easier one, while the easier one is still equivalent. In other words, those two, this is a complicated one, this is the easy one, those two have the exactly same solution set, and then that is like the basic idea of how do we solve those linear systems. Okay, so we can start with one very simple example here. So for example, if we do, I don't know, example 1, let's have x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, 5x1 minus 5x3 equals 10. Okay, equals 10. Cool. So the corresponding augmented matrix is 1, negative 2, 1, 0, 0, right? 2, negative 8, 8, and then 5, 0, negative 5, 10. Okay. So what we're going to do is we want to reduce the number of the variables, okay, and then in other words, this is a system of linear equation and 3 equations with 3 variables. What I want to do is it possible that I can reduce one variable from equation 2 and 3 so that those two equations is going to become into a 2 equation with 2 variables. It's a smaller linear equation, okay? And then we know how to handle a system of linear equation with 2 variables, and then we can mimic that idea to reduce that into 1 variable with 1 equation, and then we can solve that, and then we can substitute it back, so that finish the whole process. Okay, the whole process. So go back to here. What we can do here is, well, if we label this as, let's see, this is 1, 2, and 3. So you can see that if I want to keep the first variable x1 in the first equation and then eliminate the x1 for the other equations, and then what should we do? Well, equation 2, there is no x1, so it's easy for us. All we need to do, don't you agree, that is we can do something to eliminate the x1 from equation 3. How do we do that? Well, as you can see that this is what we can do. We can let equation 3 minus 5 times equation 1, right? And then let this new operation equation to be the updated equation 3. So if we do this directly in terms of this augmented matrix, what are we going to do? Well, as you can see, we have 5, 0, negative 5, 10, right? And then of course we have minus 5. This is 5 times this one is going to be minus 10. 5 times 1 is 5. This part is 0. Keep in mind, you might want to write into the bracket so that you don't mess up with those signs. 5 minus 5 is 0. 0 minus negative 10 become positive 10. Negative 15 minus 5 give you negative 20. 10 minus 0 give you 10. Okay. So after you drive this, if we updated our augmented matrix, do you see it's 1, negative 2, 0, 0, 2, negative 8, 8, and we're going to have 0, 10, negative 20, 10, right? Okay. So don't you agree that if I write this augmented matrix back to the linear systems, and then do you realize that the x1 on the third equation is already gone, right? But surprisingly, x2 is starting to generate it. Okay, so that's one thing. What we can do? Well, is it possible that we can do more? In other words, we already eliminate the x1 variable from equation 2 and equation 3. Now, is it possible that I can use equation 2 as the base to keep x2, but I want to eliminate x3, x2 from the third equation? The answer is, of course, we can do that. How do we do that? Well, as you expect, we can use the new equation 3, right, to subtract 5 times equation 2. So it's going to be 0, 10, oops, so it's 0, 10, negative 20, 10, that's my equation 3, minus 5 times equation 2, so 0, this is 10. This is going to be 5 times negative, this is negative 40, this is 40, right? And then I do a subtraction, 0 minus 0 is 0, 10 minus 10 is 0, negative 20 minus negative 40, that will give us it's plus 40, so it's 20, right? And then 10 minus 40 give us is negative 30. Okay. So you can see that by doing that, if we rewrite our augmented matrix, so it's 1, negative 2, 1, 0, 0, 2, negative 8, 8, we're going to have 0, 0, 20, negative 30. Okay. So by doing this, actually, you can see that the last equation, so if we write it back to the equation system, it's going to be x1 minus 2x2 plus x3 equals 0. 2x2 minus 8x3 equals 8, and then 20x3 equals negative 30. So do you realize that in this way, actually, the third equation only has one variable left, which is x3. We can easily solve x3, and then we can plug back in to solve x2, and then we can plug back s2 and x3 to solve x1 easily, right? So this is the procedure, and we definitely can do that. But one more thing I want you to think about it is what is the ideal augmented matrix we have? So for this problem, do you see that the ideal augmented matrix, do you see the perfect way is in this format, right? I mean, if we can simplify our augmented matrix into this, do you see that the corresponding system of linear equations is x1 equals a, x2 equals b, x3 equals c, right? We can directly write these solutions out. Okay, write these solutions out. So that's going to be something we might talk about in the next section. Also, a couple of things before we move on, I want you to think about here. You see, once we get out to here, we write it down. So if you observe this 2, negative 8, 8 here. There's a common factor, right, among all of this, which is 2. So if you can multiply 1 over 2 to each of them, do you agree that this product becomes into 1? This is negative 4 and 4. Same logic for the third equation, 5, 0, negative 5 and 10. Do you realize that if we can divide 5 on both sides, this will becomes into 1, 0, negative 1, and 2. Okay, so that's something I want to suggest you to do. When we talking about the row reduction and the echelon forms. Okay, but starting from here, I just want you to give you a brief idea how do we start to solve the system of linear equations here, which we want to use some elimination technique. And this elimination way is called the forward elimination. In other words, as you can see that after our procedure, for the coefficient matrix part, do you realize that it's a upper triangular format, right? Okay, so this is what we do, and the ideal one is a purely have a diagonal matrix for the coefficient. I mean, that's the best scenario if we can achieve. Also here, students might ask, okay, why you do this? Why you do this, and then how do why this part is gonna be work? So here's the thing. Let me first introduce another concept. Is called the elementary row operations. Okay, row operation. So the elementary row operation aims to apply in matrix that is the replacement. Basically, you can replace one row by the sum of itself and a multiple of another row. Okay, of another row. So go back to our original example. Do you see that? Starting from here, use row 3 to minus 5 times row 1, and then to replace the row 3 with this new operation here, right? Or you can think about this as add negative 5 times row 1, if that will let you feel better. Same thing. Number 2 is interchange. Okay, interchange. So you can always interchange 2 rows. Okay, 2 rows. Number 3, scaling. So you can multiply all entries in a row by a non-zero constant. Okay, so that's what we're trying to see. Remember, I'm saying that, okay, this row 2, negative 8, negative 8, we can multiply 1 over 2 to simplify. Same thing, we can multiply 1 over 5 for this row to simplify. Okay. And the row operations can be applied to any matrix, okay? So it's not necessary to augmented matrix. It can be applied to any matrix, okay? So this is very, very important things. That is the 2 matrices are called the row equivalent. So we have matrices A and B, we call it A and B are row equivalent. If there is a sequence of element, if there is a sequence of this row operations that, for example, transforms A into B. Okay, so in other words, all what we did here, you see, this is the original augmented matrix. After I do this row operation here, those two are called the row equivalent matrix. Okay, as you can see that it's the same thing, it's all row equivalent. And okay, so that's something we talked about here. And now a key conclusion or statement you need to have is, so if the augmented matrices of two linear systems are row equivalent, then the systems have same solution set. Okay, they have the same solution set. So that's why this is the original systems. After I do a sequence of row operation, this is another system of equations, but their corresponding augmented matrix are row equivalent. Hence, this one, and let me write here, and those two, they have the same solution set. However, don't you agree that this one it's way easier compared to this, right, to solve? So that's the main thing, okay, for this section, okay, for this section. And then there are two very, very fundamental questions for linear algebra. Is first of all, if a given system is consistent, is there at least one solution exists? And the second is, okay, if a solution exists, is that solution is a unique one or not, right? Is a unique one or not? So we will show you some examples in the next video. Okay, so I hope you can enjoy this, and thank you, and have a wonderful day.